you once that starts. There we go. All right. 2 more people in. 3 more people in. All right. So Sara Goeking is a scientist with the Forest Inventory and Analysis Program at the Forest Service of Rocky Mountain Research Station, and also a PhD. Somehow she manages to also be a PhD candidate in the Watts department, working with Dave Tarboton. And she has worked as a botanist at Denali National Park, a GIS analyst and sandbar surveyor in Jack Schmidt's lab, a field forester in 5 Western states, and an analyst for the FIA program. So her experience with national scale forest monitoring has taken her to several different countries on 4 different continents, where she helps developing countries implement forest carbon monitoring to meet international climate agreements. She's currently on detail as deputy program manager for the Rocky Mountain FIA program, and also trying to get her dissertation finished. Some of you can identify. in her free time, why does she have free time after what I want to know? In her free time, she builds cabinets out of Doug fir and skis or hikes to the backcountry yurts with her partner, Alex. So welcome, Sara. And maybe I could have everybody turn on your cameras just briefly and give Sara a wave so she knows that these are real people watching.
Thank you.
Instead of just names. Yeah, so we've got lots of participants here. This is awesome. Looks like over 50. Yay.
Cool. All right. Are we ready? Should I roll it? You
betcha.
Okay. Thanks, Karen. And thanks so much for all of you for being here at the end of the day today. Today I'm going to talk about a review paper that my advisor, David Tarboton, and I published in the Journal of Forestry earlier this year. And it's on the links between disturbance, snowpack, and streamflow in western coniferous forests. If you remember only 2 things, let's see, there we go. If you remember only 2 things from the presentation today, I hope they're these 2 things. First, that forest disturbance, even though it often results in increased water yield, it sometimes results in decreased water yield. And second, under some conditions, snowpack melts earlier following forest disturbance. And so I'm going to talk a little bit about what that might mean and why you might care in terms of post-disturbance vegetation recovery and growth. So the prevailing conventional wisdom in forest hydrology has been developed over the past 100 years or so. And it's that first, reduction of forest cover increases water yield. Second, that establishment of forest cover on sparsely vegetated land decreases water yield. And third, response to treatment is highly variable and for the most part unpredictable. So this conventional wisdom was developed mainly in paired watershed experiments. So the watershed shown here in the left is Fool Creek in the Fraser Experimental Forest in Colorado. These paired watershed experiments typically began by designating a control in the treatment watershed, and then streamflow was monitored for several years so that we could develop relationships between the control and the treatment. Then a treatment was imposed, typically some kind of clear-cut harvesting. That's what you see here. And then for several years after that, streamflow continued to be monitored, and any change in the relationship between the control and treatment was deemed to be due to the vegetation effects. So why is this? What's the effect of vegetation and of forests on streamflow? Vegetation, and trees in particular, affect the partitioning of precipitation into runoff versus evapotranspiration. So they do this by deflecting winds, blocking solar radiation, so shading. They intercept precipitation, and that intercepted precipitation can then be evaporated or sublimated in the case of snow, and they also transpire moisture from the ground. In the case of these paired watershed experiments, the question was, what's the effect of forest cover loss on water balance? And to answer that question, we have to look at the individual components of evapotranspiration. If evapotranspiration goes up and precipitation stays the same, then runoff goes down, and vice versa. If evapotranspiration goes down, runoff goes up. So in the case of these paired watershed experiments where there were clear-cut harvests, we're looking really at canopy transpiration and sublimation of canopy intercepted snow. Those are the two main factors that drove decreased runoff following clear-cut harvests in these paired catchment experiments. So other components of ET that I've listed here, these are all the main components: evaporation from the canopy, from the understory and the soil, transpiration by the canopy and the understory, and then sublimation of canopy intercepted snow and sublimation directly from the snowpack. So again, following clear-cut harvests, canopy transpiration basically goes to zero, and so does sublimation of canopy intercepted snow. So those two blue arrows going down are driving a net decrease in ET, leading to a net increase in runoff. So again, this is the conventional wisdom. This is the expected response. Over the past 2 decades, we've seen historically unprecedented tree mortality in watersheds all across the coniferous forests of the West due to a combination of drought, wildfires, insects, and disease. One way that these disturbances differed from those clear-cut harvests, they're not stand-replacing disturbances typically. So you don't see the entire canopy dying off or being removed. Within the past 10 years, even though there was an expectation that these disturbances would lead to increased water yield, studies started being published that actually found decreased water yield following these disturbances. So that was unexpected. And suggested that the ET response was more complex than previously recognized. It also led me, as a brand new PhD student, to think, okay, I'm reading all this conventional wisdom, and I'm also reading these brand new papers that are kind of going against that. And so we decided to do this review. We looked at 78 papers published after 2000 from Western North America. And those papers included both stand-replacing and non-stand-replacing disturbances. We asked many questions of those 78 studies. The 3 main ones I'll talk about today are: when and where were papers published? How did the studies characterize forests and disturbances? And then finally, and most importantly, did water yield or snowpack increase following forest disturbance? So the first question, when and where were papers published? The background colors here show the number of papers in the journals from which we drew the papers in our synthesis, and the bars are the actual papers that we reviewed. There was a big increase starting in about 2012, and I think that's increased even more in the last 2 years, so after we did this review. And when we broke them out by discipline, we looked at whether they were in forestry, hydrology, or other like multidisciplinary journals. The biggest increases were in the multidisciplinary and hydrology journals, and not so much in the forestry journals, which is a big part of the reason why I decided to submit this to the Journal of Forestry. Okay, the second question, how did studies characterize forests and disturbances? Among the 78 papers that we looked at, more than half of them characterized them categorically. So that means they characterized their watersheds as forested or non-forested or disturbed or undisturbed. In some cases, they had more than 2 categories, but still there were very few. There weren't that many studies that used quantitative metrics to characterize forests and disturbance. The ones that did typically reported them in a descriptive way. So what I mean by that is they simply said, here was the density of the forest, for example, or here was the canopy cover in our watershed. They did not typically try to quantitatively link those metrics to hydrologic response. Among the studies that did quantitatively link forest characteristics or forest disturbance characteristics to hydrologic response, they mainly used leaf area index or plant area index, and that's something that foresters don't typically record or estimate as part of their field measurements. And so that seems to indicate that there's a little bit of a disconnect between these disciplines. Okay, the big question, did water yield or snowpack increase following forest disturbance? So not every paper directly looked at stream flow. In some watersheds that can be difficult. And so some looked at peak flow magnitude or timing, flow flows, or maximum snow water equivalent, which is a big predictor of how much runoff is going to occur. Note that the total number of studies is greater than the sum across each row because many of the studies looked at multiple watersheds. And the main point here is that many studies found variable responses with lots of increases, a fair number of no change, and still a substantial number of decreased responses of stream flow and maximum SWE following forest disturbance. And even though I haven't parsed these out here in terms of simulation-based versus observation-based studies, there were both types of studies, so observations and simulations that concluded that in some cases water yield decreased following disturbance. Among the simulation-based studies, only those that used physically based models were able to simulate any decreases in water yield, and the fact that some of the observations also included decreased water yield indicates that that is a strength of physically based modeling. So when I say physically based modeling, I mean models that are based on principles of conservation of mass and energy, as opposed to more empirically based models that may be simpler, but may also have a built-in assumption that water yield increases when forest cover decreases. So next, we tried to identify commonalities among the studies that found decreased water yield following forest disturbance. The first characteristic we identified is following non-stand replacing disturbances. So again, the conventional wisdom is mainly based on stand replacing disturbances. We found that a greater proportion of non-stand replacing disturbances observed decreased water yield following disturbance. So 9 out of 19 as opposed to 3 out of 17. There were two other characteristics that we found that were common across studies that found that decreased water yield. The second one was where post-disturbance vegetation grows densely and or rapidly. So by densely, in some cases where trees were replaced by high leaf area shrubs, those shrubs had transpiration rates that exceeded the rates of the trees that they replaced. Also, there were some studies where the overstory died and the understory contained advanced regeneration of trees. And in other studies, it was actually grasses. And in a couple different scenarios, the understory vegetation did transpire more than the overstory trees had. And so when the trees died, the understory really took off and transpired a lot and overcompensated for the loss of the overstory. The third characteristic was that in high radiation, water limited environments, decreases were more likely. So at low latitudes and south facing aspects. So now I want to come back to these components of ET. And as a reminder, this is the expected response, that canopy transpiration and sublimation of canopy intercepted snow are the main drivers of a net decrease in ET, which translates to an increase in runoff. The observed response in places where the unexpected water yields were found was that evaporation from the soil, transpiration from the understory, and sublimation from the snowpack overcompensated for the decreases in the blue arrows, resulting in a net increase in ET. So now I'm going to share a few case studies that looks at these mechanisms and also kind of pivots to consider what it might mean, not only for water yield, but also for forests and for forest resilience. This first case study is from Colorado, where Joel Biederman looked at 8 catchments that were affected by mountain pine beetle. He used 3 quantitative methods to compare pre-disturbance and post-disturbance stream flow and concluded that more watersheds had decreases than increases in water yield. In a subsequent study, he used eddy covariance methods to quantify evapotranspiration throughout the year and found that both winter and summer ET increased following disturbance. So he attributed that to increased sublimation from the snowpack in the winter, as well as increased transpiration from the understory and increased evaporation from soil during summer. So this study has all three characteristics that I just described as well. So there was a non-stand-replacing disturbance, there was advanced regeneration and rapid post-disturbance growth, and it also has relatively high net incoming radiation. It's at a fairly low latitude compared to a lot of the other studies that we looked at. Okay, now I want to talk about snow and how these disturbances affect snowpack and what that might mean for forest recovery as well as runoff. So forest density and structure affect snowpack. Trees perform several eco-hydrologic functions that affect the snowpack. So first, they intercept snow, and that can reduce snow accumulation. They also shade snow, so they're blocking shortwave radiation, and thus they can serve to maintain snowpack and slow melt in the spring. Third, they absorb and emit long-wave radiation. So if temperatures are warm enough, warmer than about -1 degree C, trees also can melt snow. And which of these functions is the most important depends on the site, and it has mostly to do with aspect. So now I'll show you a couple examples where the aspect really determined what the effect of trees on snowpack was. This is a study that we looked at in the Canadian Rockies. There were clearings, two clearings, one on a north-facing aspect and one on a south-facing aspect, and similarly, two forest plots, again, one north-facing, one south-facing. If you look in this graph at day of year, about 1:15, that's right around April 1st, so that's what hydrologists usually look at to see how much water snow is stored in the snowpack. That's maximum snow water equivalent, or SWE. And first, if you look at the two clearings versus the two forest plots, the clearings have a lot more April 1st snowpack than the forests. But then, once the ablation or melt phase started, snow disappeared from clearings before forests on south-facing slopes. But on north-facing slopes, the opposite was true. So on the south-facing slopes, again, the trees are serving the function of shading the snow and retaining snowpack. On the north-facing slopes, the trees are serving the function of warming the snowpack, again, through that long-wave radiation emittance, and they're melting snow. So this is in the Canadian Rockies. It's a fairly cold site. Now we'll go to a warmer site. This is the Twitchell Canyon fire in Utah. And here, there wasn't a lot of difference between burned and unburned areas on north-facing slopes, but if you look at the two solid lines that represent the south-facing slopes, so the black solid line is burned, the gray solid line is unburned. On south-facing slopes, the burned areas had less maximum snowpack, or less April 1st snowpack than unburned stands. And then the snowpack disappeared about 2 weeks earlier than in unburned stands. So again, the trees on the south-facing slopes are serving to shade and retain the snowpack. So earlier melt means potentially faster and earlier runoff, but it may also result in less soil moisture during the growing season. Coming back to the conventional wisdom, we've kind of revised that with our current understanding. So first, that reduction of forest cover usually increases water yield, but in some circumstances, it decreases water yield. Second, establishment of forest cover on sparsely vegetated land decreases water yield. A key word here is sparsely, because we did see several studies that found that high leaf area shrubs, or in some cases, dense grassy vegetation or advanced regeneration by trees can have transpiration that overcompensates for decreased loss of canopy transpiration. So, and then third, response to both treatment and disturbance is highly variable And for the most part, predictability is improving. So we tried to identify some common characteristics among sites that had unexpected decreases in water yield. What does this mean for forest management? Silvicultural prescriptions such as fuels treatments and thinning can mimic these non-stand-replacing disturbances, and using them to increase water yield is unlikely to produce measurable success everywhere. And in fact, doing such treatments on south-facing aspects may remove that function of trees acting to shade and retain snow, and may thus result in earlier melt, so less snow retention. And that may in turn affect soil moisture during the growing season. Finally, the best available scientific information on the link between forests and water is changing rapidly in semi-arid western forests. And I use that phrase, the best available scientific information. If you haven't heard it before and you do applied research, it's an important phrase because it appears in the policy guidance for most land management agencies. Their management plans and project planning is guided by that statement. And then figuring out what is the best available science, that's a big can of worms. But in short, it's changing rapidly in this area. So how do we improve our understanding and move the science and the management forward? First, using physically based models to simulate hydrologic responses, especially in sites that have the three characteristics that I mentioned earlier. Second, identifying conditions where empirical models are sufficient and where they're not. There's a reason why people use empirical models. They're often easier to use. So as long as they're still suitable and producing realistic results, that's okay. And then third, improving the quantitative representation of forest density, structure, and composition in hydrologic models. So not just spatially explicit models, but even more simple mathematical models that relate things like leaf area to hydrologic response. So now I'm going to talk just for a few minutes about the rest of my work, my current work as part of my dissertation, where I'm trying to move the science and the management forward. First, I'm trying to tackle that piece of improving the representation of forest cover for hydrologic modeling. I'm using data collected by the Forest Inventory and Analysis Program to do this. So when I'm testing this approach in the South Fork Flathead watershed of Montana, I'm using the plot data to develop overstory and understory leaf area estimates, and then combining that data with biophysical and remote sensing predictor variables in a random forest regression model to produce maps of overstory and understory leaf area for my watershed. That does two things for me. The first is creating separate input layers for hydrologic models, so separate overstory and understory layers, and I can do this for multiple time periods. So here I have two little tiny graphics of two time periods of both overstory and understory. The second thing this does for me is allows me to look at general changes in leaf area over time at a watershed scale. So here's an example. This is overstory, understory, and total leaf area change in my watershed in Montana. Blue areas are where LAI has increased. Red areas represent places where leaf area has decreased. So the red areas where overstory LAI has decreased correspond to places where understory leaf area has increased. And those also correspond to places that we know experienced wildfires in between the two time periods that I considered here. So we're doing reasonably well at predicting known events and producing realistic results. Overall, watershed scale leaf area decreased, and over that same time period, the runoff ratio, or the fraction of precipitation that became runoff, increased. So the next step then is to use a distributed hydrologic model to see when these types of changes occur that are different in the overstory and the understory. What are the hydrologic fluxes that are determining where and how runoff increases or decreases? The second second thing that I'm doing is trying to test some of our hypotheses about where runoff is likely to increase or decrease using large sample hydrology. When I say large sample hydrology, I just mean using lots of watersheds. And I'm not going out and collecting data from all of these watersheds. I'm using existing data sets. Specifically, I'm using the CAMELS data set described in the Newman et al. Paper listed in the upper left, and then also using forest attributes from the Forest Inventory and Analysis data set summarized to the 8-digit hydrologic unit code watersheds. The questions that I'm answering here are, has stream flow changed following post-2000 tree mortality in these lots of watersheds? There are a couple hundred of them. And then in watersheds that have experienced recent forest disturbance, does stream flow response vary with disturbance severity or aridity? And aridity just has to do with what's the evaporative demand relative to the amount of precipitation. Here's what I've learned so far. On this plot, the x-axis is the proportional change in tree volume. So you can think of that as, did a disturbance occur and how severe was it? So on the right, we have increases in tree volume. So that's just the forest growing. On the left, we have decreases in tree volume over time. And the farther to the left, the more negative it is, the more severe the disturbance is. Then the y-axis is the change in runoff ratio, which again is the proportion of precipitation that became runoff. So the blue and the green dots here represent watersheds that fit the conventional wisdom. So either forest cover increased and water yield decreased, or forest cover decreased and water yield increased. So those are the expected responses. The orange, or the red and the yellow are the unexpected responses. So in the lower left, the red watersheds are those where there was a disturbance of some sort, and runoff decreased. So now if we look at those in terms of aridity, and again, aridity is the proportion of precipitation, it's evaporative demand or potential evapotranspiration relative to precipitation. And here, I found that basically the disturbed watersheds with a decrease in tree volume occurred in water-limited watersheds. So that's not a huge surprise, but I was kind of surprised how clear that pattern is. And if you prefer to think of it in geographic terms, where is this on the landscape, instead of thinking of it in terms of aridity, if you look at the map in the lower right, it just means that the watersheds that had decreased tree volume and decreased runoff are more, they tend to be across the southwestern US, Southern California, up through Wyoming. So I also want to mention the watersheds that are yellow. So there we had increased tree volume and increased runoff, which is difficult to explain. My advisor and I talked about whether that could be due to temperature affecting leaf conductance and transpiration. And what I actually found when I looked more closely at those watersheds, I found that one of the biggest changes that's occurred across all of these watersheds over time is an increase in temperature. I used a method called time trend analysis. If you're curious about the details, just take a look in the lower right. If you aren't curious about the details, that's okay. The main point is that this analysis method assumes that the relationship between precipitation and temperature and then runoff is the same through time. And so you can use a model developed for one time period and apply it to a second time period to see what change in runoff is due to vegetation effects. So that assumes a stationary relationship of runoff as a function of precipitation and temperature. And what I found was that temperature has increased, and based on daily precipitation and temperature, the proportion of precipitation in the winter that falls as rain versus snow has increased pretty much across the board. Not in all watersheds, but in general, it's a shift toward more rain falling and less snow in the winter. So again, trees intercept snow that can then be lost to sublimation, or it can be offloaded to become part of the snowpack that's then stored until the snow melt season. But when it falls as rain in the wintertime, less is intercepted, less is stored, it becomes immediate runoff and then isn't available typically during the growing season. So a take-home message here is that methods that have been developed to evaluate the effects of vegetation change may assume stationary climate, and if climate's not stationary, it becomes more difficult to identify these effects. Okay, so coming back, big picture points. Again, if you remember one thing, remember that even though the conventional wisdom is that forest cover loss results in increased water yield, in some cases, forest disturbance results in decreased water yield. And second, under some conditions, snowpack melts earlier following forest disturbance, and that might affect growing season soil moisture and thus post-disturbance recovery. A third one is that it's difficult to separate stream flow changes that are due to forest disturbance from those that are due to non-stationary climate, particularly the temperature and winter precipitation phase. So with that, I'll turn it over to Karen. I thank you all for your attention. I'd be happy to answer any questions.
Okay, well, if you're a Zoom professional, you know how to give little claps right now. So there are all the little hands appearing, yay. Okay, so we've got enough people that I think if we had a free-for-all discussion, it might sound like last night, so we don't want to hear that again. So let's instead, let's have you just either put your name in the chat box and I will call on you sort of in order, or if you'd rather type out your question and not have to ask it yourself, I'll ask it for you. So either put your name down or type up your question. Looks like we've got one from Johan. So Johan, go ahead and unmute yourself and let's see your picture.
Okay, great. Thanks for a great seminar. So you talked about forest cover in a sort of a generic sense. And from what I could see, you were looking at forest cover in terms of coniferous forest cover. So there's been some really cool work done here by Eric Lamolfa and Ron Ryle up at Deseret Land and Livestock, where they looked at the mix of forest cover. So particularly the ratio of evergreen coniferous and deciduous, specifically aspen and coniferous. And it seems that you might, if let's say you have a change in the ratio of those two functional types, you might have the same forest cover, but you've got a change in the ratio of deciduous to evergreen. And that can have a major effect on the amount of interception of snow on the canopy and therefore sublimation and therefore runoff. So could you comment on that?
Yeah, that's a great point. That's not something that we looked at in our review because most of the papers did just focus on coniferous forests, and they didn't even include any description of whether there was an aspen component. I would expect that a mixed aspen coniferous forest would respond somewhat similarly to a coniferous forest that had a non-stand replacing disturbance. Because in the winter, basically, you still have the aspen, the trunks and the branches and everything, right? And so not, like you said, not intercepting the snow. There's more wind and solar radiation are allowed to pass through. So the review didn't look at that, but where I'm looking at the use of plot data to develop separate canopy strata of leaf area, I am looking at that and using clumping indices that are different. They're specific to forest type. So they're looking at what those impacts might be, and I don't have an answer to that question, but I suspect that a mixed aspen coniferous forest would be more similar to either a sparse coniferous forest or one that had experienced non-stand replacing disturbance, with the key difference that aspen probably has pretty high transpiration rates compared to what the understory vegetation would be if the aspen wasn't there.
Yeah, so I think it's really interesting if you could look at that, because what comes into play here is the issue of ecosystem services. So obviously the quality and the quantity and the duration of water runoff from a catchment is really important for downstream users. But now if you've got a wildlife management system that is maintaining high densities of ungulates like elk in a catchment, which is being managed by one agency for one set of stakeholders, and it has an effect on watershed function, which is then imposing a cost on another set of stakeholders, then I think it becomes a very interesting issue and provides a basis for dialogue about how to manage natural resources in a wildland.
Yeah, I think you're right. And I think that the trade-offs that might exist between those different objectives that's an important thing to consider, and they might not always be entirely compatible. So, and I'll contact the people you mentioned to learn more about that. Thank you.
Yeah.
Good. We got another question ready?
I see one in the chat.
I only see Johan's name in the chat. Maybe it's to you.
Oh, it is to me. Okay, so I can read it. Can you explain again or further clarify the difference you saw for arid landscapes in terms of the water yield response, as it would apply for us Colorado River Basin water nerds? Ooh, I love Colorado River Basin water nerd questions. The main difference is that in arid landscapes, first, that's where a lot of the non-stand replacing disturbance and tree mortality occurred. A lot of it was related to drought, insects, and disease. And again, it was the watersheds with that aridity greater than 1, so potentially evapotranspiration greater than incoming precipitation. Those were the places where we saw the most mortality, and also tended to see more decreases in water yield. So if I was a Colorado River Basin nerd, which I am, I would expect that watersheds in the Colorado Basin were more likely to experience decreased water yield as a result of forest cover loss. I also want to mention that one case study that I didn't include here that pertains to this question was by Katrina Bennett. I think it was a 2018 paper. She used a physically based simulation model, the VIC model, to look at the effect of future forest disturbances. So that she took some disturbance projections from another paper and looked at the effect of those disturbances along with future climate on San Juan Basin water supply. And there was actually, when she only looked at climate, well, there was a decrease in water supply, which hydrologists have known about for a while, have been studying it and simulating it for a while. But the decrease in water supply was even greater when she accounted for those disturbance and vegetation effects. And the places where she saw the greatest vegetation-driven decreases in water yield was where forests were replaced by high leaf area shrubs. So dense shrubs came in and actually transpired more. And then soil evaporation too, those two things together, the shrub transpiration combined with soil evaporation after the canopy was lost, they were greater than the transpiration from the previous canopy had been. So I hope that answers the Colorado River water nerd question. Thank you.
Good. Looks like we've got one here from Danny Berger that says, does the type of stand replacing disturbance, in other words, fire versus clear cut, influence water yield following a disturbance? I would assume that the plant community that emerges following the different types of disturbances would be different, and this might influence evapotranspiration. Maybe you have already answered that and I missed it.
Somewhat. So I didn't address that question directly in the review, because I was really more interested in the non-stand replacing, stand replacing disturbance question. But I think it, from other literature, not the work that I've done, but it does seem like it does affect water yield response, especially when there are hydrophobic soil surfaces that are formed as a result of high severity fire. If it's truly a stand replacing fire, a lot of times it's severe enough to form that hydrophobic layer. And so water just runs off faster. So there's less time for it there's less recharge, there's less that percolates into the soil that can be available for evaporation or transpiration. So it's not only a greater proportion of precipitation becoming runoff, but it's also the timing and the rate. Following fire, there's also the concern about sedimentation. So you're likely to have earlier peak flows, larger peak flows, more sedimentation. And the sedimentation, the projections that I've seen in some papers are not trivial. And I suspect that that's going to be a concern for water managers in the future.
Good, thanks. There's another one here. How does the ET ratio vary between the different undisturbed forests?
So the ET as a ratio of precipitation or evaporation relative to transpiration?
Martin, you'll have to clarify that one if you're here.
E relative to T.
Yeah, E over T.
Man, I wish I could answer that question. I really do. I wish that there was more information, and I wish I had that information. That is difficult to disentangle. For many years, the only way to even quantify ET at all was using a water budget approach. So trying to close the water balance, looking at how much precipitation fell, how much left the watershed, and then using the difference. You can add some other terms into that water budget, but that's the basic approach, and that only gives you total aggregated ET. It's only since people have developed eddy covariance methods and also somewhat isotope measurements have people been able to separate what those different components are. And so I don't want to venture a guess as to how much they differ. I do know that, I have seen some recent research suggesting that there's a lot more transpiration and a lot less evaporation, and this makes sense in energy limited watersheds as opposed to water limited watersheds. So again, thinking about that aridity scale that I showed, the places that have aridity less than 1, they're energy limited, not water limited. So there, the evaporation is probably a lower proportion of total ET, whereas in the higher aridity forest types, undisturbed forests, transpiration's probably it could be a bigger proportion. That's me venturing a guess.
Good, thanks. I don't know if you see any more questions right now. Ola, here's a couple more. Let's see, sap flux measurements may be something to look into, suggestion.
Yes, that's a great suggestion.
Good,
from yes.
The advisor, so that's good.
Yeah.
Okay, I know that if there are no more questions for Sarah, she's got some for you.
I sure do. So
stay tuned.
There's a lot in science, where you ask a question and it leads to more questions, right? And I think I really like throwing questions out to people in different disciplines and hearing, their take on something that I've been working on, or offering my take on something they've been working on. So I talked to Karen about trying to make this a little more interactive. And so now here's a set of questions to which I do not know the answers. And I know that this is a really diverse group with lots of different specializations. So I have several questions here, and I've just roughly divided them up into wildlife, range, forestry, ecology, hydrology, and climatology. So I can read through them, or if anybody wants to jump right in to offer their take on any of these questions, that would be awesome. But the first two, so wildlife and range, you know, Karen and I talked a little bit about this idea of the green wave, that when snow disappears in the spring, there's sort of this phenology that moves across the landscape. And, you know, I think, okay, if snow is melting earlier, does that mean that semi-arid landscapes are also going to have a brown wave that follows that green wave? So the questions here, if severe forest disturbance results in type changes from forest to non-forest following a disturbance, what cascading effects might occur within food webs? And might there be any effect on diseases? And then another vegetation effect would be how herbaceous communities might be affected, whether you might expect more invasives.
So we'll handle these just like we did questions. Don't hide in your Zoom window. If you've got some thoughts on these, just put your name in the chat window, or you maybe just pipe right up.
I would love to hear some wild speculation about any of these. Not just constrained to the first two, you know, the forestry question too, what types of climate adaptation strategies might mitigate disturbance-induced type changes.
Okay, looks like Johan might have something to say, hopefully about the wildlife one.
Awesome.
Yeah, sure. Can you hear me?
Yes.
Yeah.
Yeah, so with regard to the green wave, brown wave, there's a group of us here that's actually just got a paper in review right now on that, where we found that although there's been a lot of discussion, a lot of mention about how important the green wave is, it turns out that the brown wave really is very important in terms of determining pregnancy in elk. So the duration at which the landscape remains green is crucial. And if the brown wave comes early, then the animals go into the winter in poorer condition, and elk cows are more likely to either not conceive or to lose a pregnancy. And the yearling elk are less likely to reach reproductive status the following year, in years in which the snowpack conditions and presumably forest cover conditions cause an early brown wave. So I would predict that if you have a large scale transition of forest cover such that you get an earlier brown wave, it would certainly propagate into the demographics of wildlife on that landscape.
Interesting. Did you use the phrase brown wave in your manuscript?
We did.
Nice.
Cool.
You thought you made that up.
I did. Well, and I hadn't been following that.
Well, we talk about green up and brown down, and the green wave and the brown wave.
That's fascinating and really kind of depressing too, but it's something that had not occurred to me.
Yeah, and so there's a positive result with pregnancy rates in elk female using NDVI to monitor the brown wave.
Interesting.
That is interesting.
Anybody else want to weigh in on the wildlife question? Yeah, maybe you can move on to some of the other ones.
Yeah, so the range, and for any of them are fair game. I'll get down through the rest of them and then just kind of open it for any or all. So the ecology one, how might this affect biogeochemical cycles? That's something I've thought a little bit about, but not a lot. I certainly don't know the answer to this. And then in hydrology, what mitigation strategies should managers consider as disturbance regimes might intensify? We're already seeing this in some places, and that can potentially affect both water quantity and quality. And then in climatology, if there's warmer temperatures and a coincident shift from snow to rain, how might changes in the magnitude or timing of hydrologic fluxes create climate feedbacks?
Good question. Okay, looks like Chris Traft, you want to go?
Yeah, so I was just thinking about the climatology issue, and I know it's widely, the prevailing wisdom right now is that with climate change will decrease snowpack in western forests, and so with less snow, that could mean snow has a higher albedo, so the albedo effect might lead to more warming, and that might be a positive feedback loop there. And also with warmer temperatures and with snow melting earlier, you could perhaps have a longer growing season. And I'm not sure what effect that could have the effect on more understory, more herbaceous vegetation, and then perhaps that could increase transpiration through the understory, and then that might even further decrease water yield, which there's already less water yield because of less snowpack, so that might be another positive feedback loop.
That's a good point. And so and to piggyback on that, if you have more transpiration, would the change in latent heat flux then, would that have an impact as well?
Perhaps.
Yeah, the albedo, I think the albedo effect that's a really great point. And I've seen at least a couple papers that looked at that. One in the Colorado Basin that did find that has an important effect on temperature and evaporative demand. Yeah, thanks for that, Chris.
Hey, any others? There are lots of questions there. Lots of people here. Okay, well, I guess we'll let it sit there then. I think these are all really good questions for future study in these various fields. I think that's a really great way to link these up.
Yeah, well, and I enjoy. Okay, there's a question. I got a question just to me, so I'm gonna instead of trying to type it, I'm just gonna read it. Who was the author of the San Juan study I mentioned? It was Katrina Bennett, and I think it was published in 2018. I'm not remembering the name of the journal, but there were some pretty dramatic conclusions right in the abstract, and she used the Vic model, and I think there was just one big study that looked at that. Okay, I appreciate everybody being here again, and especially the people that were willing to show their faces and engage. And even if you don't engage here today, keep thinking about these questions. Yeah, Karen and I were both part of a forestry discussion group that was meeting once a month until, well, in the before times. And I got a lot out of just asking or trying to answer these kinds of questions, and I think it's just kind of a good thought exercise too, and it's fun.
Good. We may try this again with another seminar down the road and see how it goes. So, all righty. Well, Sarah, thanks again. That was a really great seminar, and maybe if you have a chance to turn your camera back on and give a clap, that'd be awesome. Nice.
Thank you all. Have a great Wednesday afternoon.
Yep. Thanks again, Sarah.
Yeah, thank you, Karen.
Yep. Bye.
Bye.